Hello, welcome again. This is a continuation of my series where I do the 2025 Everybody Codes Challenge long after the challenge has already come and gone, but you know, it's new to me. All these problems, these are the first time I'm hitting them. I'm going to start the timer here, but I'm not going to start Quest 10 yet, because first of all, I want to go back and optimize Quest 9. If you saw in my video where I did Quests 8 and 9, I'll try to remember to put a card up there to link to it. Quest 9, my final solution, took a little bit longer than I would like. So I'm going to go back and see if I can speed it up a little bit. So we'll do that first. I am, however, going to start this timer here, and because the timer is mostly how long have I been working, and it's supposed to keep me from making these videos entirely too long. I mean, they're already over an hour, some of them. So, right, anyway, let's get on with that. Let's go back and look at Quest 9 and see how that could be optimized. Now, I think that Quest 9, first of all, I'm reasonably sure that the slow part of Quest 9 is in problem 3. And more than that, I'm reasonably sure that it is in this loop here. Before I do anything, I'm just going to test that a little bit. And I'm going to test that in a very crude fashion. So okay. Unfortunately, testing it in a very crude fashion requires golang that I don't know off the top of my head. Timer. Time.now, time.set start. Okay, that's all I wanted. Now, print line. Start time. Okay. Then right. So time for equivalence class loop took really? Well, that is a little bit surprising. Let me see what happens if I move it back to up here. Okay, so, well, good about that. I was completely wrong about where the time is going. This is a lesson to me. I should this is a note to me that I should not assume things about where we have stuff located. Okay, so so all the time is being spent here in this loop where we are finding parents. I guess that's not unreasonable. We go through every possible scale saying if this is the child, find two parents that could be parents. It's almost certainly faster if we could find a way to accept or reject triples, because we don't really care who's the parent, who are the parents, and who's the child here. All we care about, just a moment. All we really care about is that those three are connected. So what we could do is if we could come up with a function that would just tell us, given three different scales, are they connected? Okay, sure. Let's func is family. I could do three different strings, but you know what, it's going to be easier to do three different bytes. A, B, C. So those are three different scale specs. And here I want, okay, three different scale specs of that. Now, yeah, I'm pretty sure it's going to be default return true. We're going to try everything. So I guess what I want to know is if the so child could be a child, and these are overly verbose names, but whatever. For AX, and then if A is not equal to B or C at that point, A cannot be the child. Yes, okay. If eval child could be A equals child copy A and eval C B B C okay, so I think that yeah, Go is mostly not white space sensitive, except that they really don't like those line breaks there. Okay, so let's connections here. 0, 1, 0, okay, then what we do is here we say this is we don't care about any of that. We just say if is family okay, if is family scales bracket idx 0 scales bracket idx 1 scales bracket idx 2 connections append idx 0 idx 1 idx 2 46303. Okay, and that got even worse. Okay, that's much better. So bail fast. Bail as soon as we've got thing there. So I might be able to speed it up a little bit more. So the time for finding the parents loop is because to find that three things match in a family is the slow bit. So I might be able to speed it up a little bit more by finding an index where 0 and 1 mismatch, and then checking 2. If 2 doesn't match there, just don't even bother. Actually, is that a solid way? So no, I still need to check. I still need to check all three possibilities, I think. I don't think I can just bail. I don't think that only checking. Okay, sorry. What I'm going through here, what I'm debating in my head is, if I have an index into the scales where all three are different, definitely these three are not part of a family. What I am debating is whether every set that is not a family would give me that, and no, that's not true, because if you have, that's not true, because you could also have not a family by having AAG, AGA, GAA, because then the first thing says that, because it's possible to have three scales such that at no index are all three different, but also you don't have a family. Okay, so I'm still going to have to do the full is family check, but this might be faster. plus if if then and okay. This will probably speed it up. And it did not. Interesting. Okay, I guess I'll just have to live with that. But I did get it under a second, so that's really what I wanted. Yeah, I'll keep thinking about that. Okay, that's all of that time gone. So on with quest 10. But not before I create some boilerplate. Quest 10. Okay. Okay, and now here I'm do that, and that's what I'm going to do for the basic things of do problem 1 and do problem 3. Yeah, do problem 2 and do problem 3, I mean. 3 and 2. Okay. And I don't know if I'll need that. Okay, so this will be quest 10, 10, 10. Okay, and this will be my boilerplate, and I will just keep incrementing that. Okay, here we go. faces. Family connections based on come from the Dragon Duck clan. Distant kingdom of Algorithmia. Okay. Blacksmith. Dragon chess tournament. Chess is played on a rectangular chessboard. The size of this chessboard can vary depending on the game. There is one dragon figure, sheep figure. Same square of the board, sheep figures. Dragon moves exactly like a knight in classic chess. Okay, so 2 squares. Okay. How many sheep are within the range of 4 moves of the dragon? Okay. Right. Okay, so the notes will be something like that. Okay, how many sheep are within the range of 4 dragon moves? Okay. Okay. Board. Clone. Scanner up bytes. Okay. Now we need 4 moves. So a move is 2. So there are 8 possible moves. And we need to know, we need to know which of those have sheep. Okay, so actually what I'm going to suggest is that instead of this, what we do is we make the board a map from coordinate to make the board a map from coordinate to byte that is what is there. So type coord struct x, y, int map coord byte, and what we're going to do is we're going to say row okay, and now we're going to val, and then if val is D, it is a capital D, correct? Yes. D, then dragon row column. Okay. Now we need a set of everything that has. Now we need to go 4 out. Okay, so okay. Within the range of 4 moves of the dragon. Okay, so that includes the one that includes like going. Yes, so we include 4 or fewer moves. Okay. Sheep eaten is a map from make map chord to bool. Then okay, so yeah, possible moves go up by 4. Okay, for range 4 moves make for yeah. Okay, then for how do I want to, yeah, for var chord -1, -2, chord -2, -1, chord 2, chord 2, chord 1, 2, 3, 4, 5, chord 2, 1. Jumps. Range jumps. Can I call it a const. Nope. Okay. Oh. Yeah. Okay. Make map from coord bool possible moves dragon true for make map bool coord jump.x plus if board bracket test s sheep eaten true and then okay, that should work. Okay, I got my thing, I moved it over, go run quest 10. 10? Really? I don't trust that number. I'm going to copy this. Okay, and now save this into input. B1 samp. Okay. Q10 P1 samp. Yeah. So they have 27 sheep, and I'm only finding 4. That's not good. Also, because I'm going like one thing further than they should. Okay, so first off, I do that. Dest equals true. Okay, let's check this out. Print line, sheep eaten. Okay. Ah! Okay, now that says 40, which is obviously too many. But now if I do that, 27. Is that what they said? 27. Okay. So now that I have that going correctly, 160. That sounds better. 160. Yay. Okay, that took me way too long. Oh well. Veronica, running through the corridors, it's hard to tell all the rules precisely. Sheep, in their turn, simply move one square, always towards the bottom of the chessboard. During the game, the moves alternate dragon, sheep, dragon, sheep. There are hideouts on the board marked as pound, which protect the sheep from the dragon. Both the dragon and the sheep can move over them in the usual way. The sheep is not eaten and can move in the next turn. Okay, so the dragon just pauses there. The goal of a sheep is to escape the board before the dragon eats it. If the sheep reaches the lowest row of the chessboard and moves again on the next turn, it can be removed from the board as a survivor. You imagine a large chessboard with plenty of sheep and hiding spots, your notes, and you try to simulate the game. 20 rounds to see how many sheep can be eaten in all possible variants of dragon moves. All hideouts are empty. Assume the sheep are not very smart and then no turn. Ah, 3 rounds of game. Right. So, okay, so we have, yes, possible dragon spots. Sure. Right. Okay, so okay, so how do I simulate okay, so if it's there, we obviously forget it. If it is okay. So I will remember the board initially, and then I will just keep track of the round number by going up. Ugh. Okay, and now I have to alternate dragon, sheep, move, dragon, move, sheep, move, dragon, move, sheep, move. Okay, dragon moves first. So zero, and then sheep is there or one above, and the dragon is not on a pound, then we have eaten that sheep. Yes, and we can say the sheep, we can keep track of the sheep we eat by keeping track of the sheep's original coordinate. Okay. Now, okay. And if the dragon row is, yes, if the dragon row is bigger than, if the dragon row is equal to that row number or larger, then we discard that one. Okay. Sure. No problem. Okay, now, how many moves are we making here? Dragon moves. Okay, so what? Let me. Sheep, both the dragons. Yes. Okay. Right. So, sheep is not eaten and can move in the next turn. Okay, so range 20 for P 20 rounds. 3 rounds. Okay, yes, okay. So, previous sheep moves. Possible moves. Okay, now dest is not equal to that. Sheep. Okay, so it'll be the row dot x minus it's not a hide, then it doesn't matter. New dragons. Okay. And I think that'll work. Part 2. $17.39. Yay! Okay. Part 3. Small. Consider 1, 2, 3, starting from the top row. Each column has a letter A, B, C starting from the left. Dragon moves to a square with a row 1 and columns A, D to A1. In the played variant, the game begins with the sheep's move. Each column can contain at most one sheep. Turn, only one sheep can move, not all of them at once. The sheep are smart enough to not move to a square occupied by the dragon, unless there's a hiding place there. Okay, if at least one sheep can make a move, then a move by the sheep must be made. Otherwise, the sheep's turn is completely skipped and the dragon takes the turn again. Dragon must always make a move on its turn. Dragon chess tournament is not about playing games. Each dragon, sheep, and hiding places. All hideouts are empty at the beginning of the game. Whoever finds the highest number of unique sequences of such games. Sequences of moves in which the dragon eats all the sheep. Okay. Each column contains only one sheep can move. Chessboard with the initial arrangement of dragon, sheep, and hiding places. All hideouts are empty at the beginning of the game. Sequence of moves in which the dragon eats all of the sheep. so we need to find the number of sequences in which we need to find the number of sequences, not all of the sequences, because good lord, we can't count that. Okay, so how do we, okay, so first of all I'm going to download this, and I'm going to take a look at the input just to see what we're dealing with here. Okay, so that's the kind of thing we're dealing with. So, I think then we only care about sequences where the dragon eats all of the sheep. Any game in which the sheep get to these hides, it's just game over. The dragon can't, well, okay, from those hides there is still a possibility. But any game in which the sheep get to those hides, it's just game over. And I think that it's worth optimizing that. So, okay, so we have to, oh man, this is going to take a while. This is going to take at least another 20 minutes, maybe another 30 minutes. Well, this is going to be a long video, even though I'm only doing one quest. Well, the quests should get harder as time goes on. That's what happens. Okay, and I did blow 20 minutes, 25 minutes on optimizing number 9. Okay, so if the sheep has gotten to a spot where there's nothing more to do, then it's game over. So I'm going to want a sequence given a dragon location. Given a dragon location and given an array that says where the sheep are. Given a dragon location and an array that says where the sheep are, determine how many things. Okay. So, do problem 3. Okay, so that's that. Okay. So row is the max. Type. Okay. Memo colon equals make map from key Okay, I can't do a star. I gotta do a... Ah, god damn it. Okay. The sheep are going to be at -1, -1, -1 for everything else. Max sheep. I don't like this. I wish I could avoid this, but I'm not going to. And sheep 0. Else if sheep and sheep chord row C and sheep plus plus. Okay. Yeah, and we'll just blow up if we have too many sheep. That's fine. Okay, and then no. Then what I do is I do n moves dragon chord sheep sheep, max sheep, chord, memo, map, okay, 64, board, map, board, byte, uint, 64. N sheep int row call. Okay. And moves. State is new memo key of dragon sheep memo board and sheep row call. If ants, comma, okay, memo if ants, okay, ants, okay, so then we have to move for every possible and then we're going to add to it memo of state. Okay, now for range jumps. Okay, so first we have to consider can the sheep move? Oh shit. I have to check no. Yeah, and we can't do that. We have to do max calls int. do. Okay, yeah, and we're not going to pass in end sheep because that's not relevant anymore. Okay. So first I have to make a sheep move. Then I have to make a dragon move. Yeah. Okay, so first I make a sheep move, then I make a dragon move. Four. Okay, so make a sheep move. If state.sheep oh shoot, we got to do all of those. End moves. So yeah, I have to do end move sheep. Yeah. So the memo is only going to be like it's the sheep's move from here. And if there's no sheep, return, there's just one spot to get here because the dragon must have eaten the last sheep on the previous move. Yes. If state.sheep of C sheep of row no, I can't do this right, because like suppose the sheep doesn't escape. Okay, so we have Okay, so any shape. Otherwise, in moves dragon memo. Okay, except that the state is not the state. N memo key of dragon. Slices dot clone sheep state dot sheep. How do you clone a... Seriously? Yeah, no, I want... Oh, wait. No, direct assignment will work. Direct assignment should work. Yeah. End state dot sheep bracket C okay, so if there are any sheep, this sheep means sheep escape. Now, if dragon state.dragon.row, no, column equals C, and if the only possible move is going there, yeah, and state.cheap equals state.dragon.x, okay, if not any sheep, if we have not found any sheep, then answer is equal to 1, because there's okay, now invent this function. Create that function and state move that. Yeah, fine. Now, in this, you had 64 of 0. For jump, range jumps, equals chord state.dragon.x plus jump.x, state.dragon.y plus jump.y, if ndragon.x less than 0, I know. If board is not a pound, then if n sheep if n sheep bracket n y sheep got eaten. And move sheep of memo key and dragon and sheep memo board row call. Okay, that is yeah, whatever. That is entirely too complicated and took me a way long time, but let us see where we are here. I'm going to try one of these sample things. Okay. Okay. Q10. Oh. Right. Okay. I have more. Shoot. I show more than they do. Okay. Okay, so let's try the smallest sample we can. Okay, I show 18, they show 15. Therefore, I have a screw up. 18, they show 15. Okay, so they show 15. Okay, so the last move is either drag into B4 or drag into C4. Okay, so one, okay. Okay, so once we get the sheep down to into 2, once that first sheep is in 2 or 3, nothing happens. Okay. Two or 3, nothing happens. Okay, let me just show the ones that are greater than 0. Okay, so 2, row 2, so that would be row 3, so that would be B3. B3 and B4. Okay. So okay, so from and the other one where all of the sheep are eaten, so C4. Okay, so the only ones that we get to where all of the sheep are eaten we also have a final thing where everything gets to one, 0. The last dragon move. Is actually to, what is that, B1? No, that's A2. No, we get an A2, and that's okay, because there is an A2 path. Okay. So the question is, why do we end up with 18, whereas the real answer should be 15? Okay, I'm going to have to write down this sheep state here. Okay, so let's say that we'd first do the sheep to A2 move. So first off, we start out with the sheep at 0, 0, 0, and then all negative ones. Yeah, we start out there, and we first do that. So 1, 0, 0, all negative ones, negative 1, negative 1. Okay, so there should be two different things that have 1, 0, 0. Actually, I guess it was just one different thing. Okay. Sheep goes to dragon goes to row 1. Sheep goes to A2. Dragon goes to... Okay, so sheep goes to A2. Oh, shoot, there are a lot of things, actually. Okay, so let's look at this. Sheep goes to C2. Let me look at sheep goes to C2. Because sheep goes to A2, there are too many of these. So sheep goes to C2. So we have 0, 0, 1, and then a bunch of negative ones. So 0, 0, 1. Actually, hold on. sheep. Okay. There. Now, okay, so sheep goes to 0, 0, 1. 0, 0, 1. Are there any other sheep going to 0, 0, 1 out there? There are not, and there should be just one possibility. That is correct. Okay, so how many possibilities should there be for B? There should be 1, 2, 3, 4, 5. Okay, so sheep goes to 0, 1, 0. Okay, wait a second. 0, 0, 1 is to C2, and then dragon goes to C2. Why is that sheep not dead? Why is that sheep not dead? That sheep should be dead. Okay, is that a hiding spot? Ah, that's a hiding spot. Okay. Okay. Sheep number 2 goes to 1. Dragon goes to 1, but that's a hiding spot. So, okay. Okay. So anyway, we were back looking at this. So B2. So there's 4 possibilities here and another one there. So we should have 5 total possibilities that have either 0, 1, 0 or possibly a 0. No, because the dragon can't immediately kill that sheep. So 5 possibilities from 0, 1, 0. So that's a 0, 1, 0. That's a 0, 1, 0. Well, that's wrong. Okay, and that accounts for my extra 3. Okay, so this is 0, 1, 0 if the sheep goes to, the sheep moves in column B first, and the dragon goes to C2. Remember to read this right, column, row, C2. And then this is A2. So what this is saying is that the dragon goes to A2. If the dragon goes to C2, there are 2 possibilities, and that is, in fact, sheep goes to B2, dragon goes to C2. There are, in fact, 2 possibilities, and that might. But sheep goes to B2, dragon goes to A2. My code says 6 possibilities. Their code says only 3 possibilities. Okay, so sheep goes to okay, so what, first of all, sheep to B2, dragon to A2, sheep to B, the next, all of them, all 3 possibilities have sheep to B3. Okay, so I'm going to do a second level debug of that. If Okay, so what am I saying? If dragon is 0, 1, date dot dragon one comma 0, sheep can we not? Seriously? Okay. Now, sheep.debug of. Okay, so sheep to B2, dragon. Okay, so if dragon is going to run. Okay, so we've a couple of those. Okay, so sheep to B2, dragon to A2, then sheep to B2, dragon to A2, sheep to B3 also gives us 1. Sheep to B2, right. Sheep to, okay, so this is sheep to B. Okay, so we have okay, so first off, I don't understand this because we should have tried both of these and we should be adding them and we should be getting that. So that's just weird. Oh. Okay. That's an explanation there. Okay, so this says sheep to B2, drag into A2, sheep to okay, so the only things we should get are from sheep to B3. So let me try. We try from sheep to B3, we get 2. And from sheep to A2, we get 3. Now, sheep to A2 at that point should not work. Okay. So this is a problem. That if the dragon has to move, and we've done dragon to A2. Wait a second, dragon to A2, and then sheep to A2. That shouldn't happen. So skip moving it. I mean, I say right there, skip it. Now, I'm treating okay, so if the only possibility is, if the only sheep I find, okay, so if the only sheep I find is oh, so don't move it. So don't move it. Else. Okay. Oh, no. Okay. Found blocked. the state memo board row column, except that I don't want to do that. I want to say if all blocked, all blocked. All blocked false. All blocked false. If state $15. Okay. Okay, now let me try the big sample. Okay, yes, that all looks very nice. Okay, big old number. Huh, I wonder if there's something about like larger numbers take longer to... What? Seriously? Okay. If the Everybody Codes website is having issues, that's not good. Great. So maybe I can't do Quest 10 because the Everybody Codes website is broken. Yay! Okay. Whew. Wow. Okay, so 2 hours on this. A lot of corner cases here. Yeah. That just took way too long. I probably set stuff up a little bit more complicated than I needed to. I think I wound up in a good place by the end, but it took me quite some time to get there. Still not happy about this max calls sheep. I really wish I could do this with some other... I really wish I could do this without this hard-coded constant in here. But Golang does not make that easy to deal with in their state, in their map. I'd probably have to implement some kind of strange interface over memo key to make it all comparable, and I don't want to do that. Yeah. But because I started this by checking the time, let's check this time. Now admittedly this time isn't great because I'm still running OBS to record, but it is under a second still, so that's good enough. Okay, let's get this added here. actually git commit. That's 9. Keep 10. Okay. And thank you. I will put links above to the other things in this series, and hopefully I will have time for more of these later this week.